We're asked to prove that we can create an isosceles triangle by folding a piece of paper. We're told that we take one corner and fold it on top of the other opposite corner, and we call this XY. So here is a diagram that shows this in action. We've got A, B, C, D for the piece of paper, and then what we are doing is folding C onto A. And I'm not showing here what the actual the result is of that, but when we unfold it, you can see that there will be a fold as just like this. So this is a question where you really do need to get a piece of paper and fold it, I think. Now, something else happens if you look carefully, and that is that when you fold it, the line CX ends up being on top of the line BA. I'm just going to draw that in. Maybe I should do it dashed as well. So this is actually, yeah, it's not part of the original piece of paper. It's not a folded line. Let me do it dotted. So that ends up, as I fold it, it ends up being along here. And there's quite an important consequence of that, because what it means is that these two angles are the same. The folded line is essentially, it bisects the angle. So the first thing we can say is that angle AXD equals angle CXD by construction. You just have to convince yourself of that. If you're unsure, then draw a pencil mark going from C to X, put the fold back in, and you'll see it lines up perfectly. Now, another consequence, well, sorry, not another consequence, another mathematical fact is that because these two lines are parallel, then this angle is also the same as AXD. Angle AXD equals angle CYX because they are alternate. Let me just highlight the Z. There we go. And what that means is that angle CYX is going to equal angle CXD because AXD is equal to both and they must be equal to one another. But these are in the triangle CXY. These are two angles in triangle CXY. So triangle CXY is isosceles. Sorry, that's my spelling here. And that is it. If you can spot that, this question can be very, very quick. Here's one other way to do this question. So we could do the fold from C to A and then draw it as it looks to us after we folded it. It actually looks like this shape. We've got X and Y, and remember we're interested in CXY. So I'm now going to draw that dashed line in just like I did before. Oh, sorry. Okay, so I want to show that CY is the same as CX. Well, we can definitely say that this length here is the same as this length because when you look at the piece of paper, remember is it a rectangular piece of paper? I can't remember if it's A4. No, it's just rectangular, but because it's a rectangle, those two must be the same. You can just see that by unfolding it and looking at it. But there's something else that's the same because it must be that these two lengths are equal. By the way, you need to make sure you're writing this down. It must be that CD equals AB because it's a rectangle. But I'm also saying that YD must equal bx. It's a little bit less obvious, but if you turn the paper round and then do the fold again, you see that essentially there's rotational symmetry. So if you turn it round, this becomes yd. So I'm just going to say bisymmetry. And because we have a right angle in both, then we can say, therefore, that cx, we can use Pythagoras' theorem, by Pythagoras is theorem on triangle CDY and triangle CBX, CX equals CY. Because I'm doing a squared plus b squared equals c squared, but I've got the same a and the b for both. In fact, we can go one stage further and say that they are congruent triangles because we have two sides and an angle in between. Side, angle, side. In this case, it's 90. And that is actually enough to say that they are the same, which means that the hypotenuse is the same. But I've done it, also by using Pythagoras. And that is enough to say that therefore triangle CXY is isosceles. So I don't know, is this a bit more messy? I'm not sure, but it's an alternative approach to doing it and to show that we do construct this isosceles triangle. Well done.